you scan from here to here, and you read off the symbols under all the heads. So it'd be W1 blank 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 blank. Okay. So the first pass, you're reading what's under the heads. Now, why do you do that? Well, because you're going to plug in those K symbols. Okay, this is the first one, the second one, the third. So in other words, W1 blank blank. You're going to plug in those K symbols and the start symbol. Sorry, the starting state of your machine. You'll plug that into the transition function for machine M. The transition function for machine M, and it will return three things. The next state, so QJ. It'll give you K symbols that will be written by each head. So call them Bs. So you have B1, B2, dot dot dot, BK. Okay. So B1 would be written here, B2 would be written here, B3 would be written here, and so on. Okay. And the third thing that the transition function will return will be K, left or rights, or stay puts. Was there a stay put? Yes, there was. Okay, so the transition function will return K move symbols, for each head, and so then okay. So you scan through. You find all the symbols that you find the K symbols under the K heads, right? And you know where the head is because of the dots. Right? Those symbols are dotted. So by scanning from here to here, from the first to the K+1th hash symbol, you will have a list then of K symbols. The symbols under the K heads. Okay. And now then you do a second pass. So you go back and then you scan through again, and you update the tapes. So you do what so you use the transition function, like I was saying a bit earlier. You look at those three things that the transition function gives you, given the current state and the symbol that the head is over, for each tape in M, and you then modify. You then write that the symbol, the B symbol, if you like, given to you by the transition function. So you'll overwrite that by something. You'll overwrite this by something, and so on. Okay. So you update all these strings. So you're updating the whole tape in S, big S. Right, so that's that. Okay, so that's essentially it. That's the guts of it. Now there are a few complications. That's what 3 is sort of about. But that's the essence of it, right? You scan across each time. This is in stage 2. You find the symbols the headers are over. You use those symbols. You plug those in, the current state plus the K header symbols, if you like, head symbols, into the transition function. That will return the next state, K symbols to be written by the head in their current positions, where all these dots are, and K moves, L or R or S for each head. Okay? And so you then change the position of the dots appropriately, for each string, for all K strings, and you just keep doing that. Now there may be a complication. What happens if S moves its head to a hash symbol. See what do you do then? So we're going to the right. Right. Okay, so so if you're moving one of your heads to the right, okay, and you move it onto a hash symbol, well, what do you do? Well, you that would correspond in machine M doing that. So when you're simulating machine S, when like for example when this dot is, well, so this head here, so it tries to move here onto the hash. Now on machine S, so that would correspond to in machine M that the head in machine M on that tape, the corresponding tape, has moved outside the string. It's now over the first blank. Okay. So what you do is in string S to do the same thing is you write. So say you need to move from here to here. So you're now over. You're moving right, and you're now over this hash. So what you do is you overwrite this with a blank, and you shift, including this symbol, you shift the whole thing up one position. Okay, and you do that every time you need to do that. So that's how the strings here can get bigger, right? So that's all that this is saying. Okay, stage 3. Yeah, that's yeah, which is down to here. It's just what I've been saying, right? So that's effectively how you get a single tape Turing machine to simulate, and hence prove to be equivalent, a K-tape, a multi-tape machine. Okay, and this would work. So in other words, you've got the single tape machine behaving in just the same way, and hence has just the same power. Recognizes the same category, set, class, whatever, of languages as the multi-tape machine. Okay, they're equivalent. They have the same power. All right. So that's well now. Implementing stage 2, if you actually start writing out in detail, all the states you would need and the transitions you would need, transition rules, and a lot of work. So as has been said several times, it's unusual to see a full, I mean truly full, formal definition of a Turing machine. There's just too many details. It just gets too tedious. Right? It becomes a major headache and a major task. So usually you stop with a relatively high level description of how it works, enough so that you can see in principle how to do it. And then if you really wanted to, you could then run with what the high level explanation that you're given, and fill in all the lower level details, and you may have to go down several levels. Okay, right. So assume that's that theorem has now been proven. What was that? It was theorem 3.13, I think. Theorem 3.13. Every multi-tape Turing machine has an equivalent single-tape Turing machine. Okay, so assume we've proved that. Now there's a corollary. Remember, a corollary is just a kind of after theorem, usually fairly simple, that follows fairly quickly and easily from the preceding larger, heavier proof. Okay, so here's a corollary. A language is Turing recognizable if and only if some multi-tape TM, so multi-type TM recognises it. Now that may seem fairly obvious from what we've done before. So we've done a theorem previously. A language is Turing recognisable if and only if some Turing machine recognises it